Hi everyone. Today we'll do some work looking at the work of two scientists, Louis de Broglie as well as Verner Heisenberg, and we are going to look at their studies of something called matter waves. So to date, we've talked about light, and we've talked about light having a dual nature, meaning it can look both like a particle and like a wave. And so some scientists started to wonder, well, wait a second, if this is true of something like light, where waves can have particle-like properties, then wouldn't particles maybe be able to have wave-like properties? And so one of the people who started studying that was a guy named Louis de Broglie. And what he did was that he proposed that all of these things that are moving around, what we would call matter, they all have wave-like properties. So not just the idea that waves can have particle-like properties, but the opposite, the idea that particles can also have wave-like properties. And he called these matter waves. So his research actually led to a whole lot of really interesting discoveries that we use today. So things like X-ray diffraction and electron microscopes came out of de Broglie's work. Here are some images that came from an electron microscope. And you can see they can go really, really small in terms of what they're able to pick up and what they're able to see, much more than the microscopes we might use in bio class or something like that. De Broglie also has some equations that go along with him, but they're really just a culmination of a bunch of other equations that we already know. So for instance, we know from Einstein that energy equals mc squared, where m is mass and c is the speed of light. And we also have talked about the idea that energy is equal to h nu, and h nu, remember, nu is frequency. And so if we combine all of that, remember that energy can also be combined in this form, because we also know, this equation is missing here, but we also know that C is equal to lambda nu. So if you combine C equals lambda nu and E equals H nu, we get energy equal to this product over here. And then if you put all of that together, it turns out that MC is equal to H over lambda. So said another way, mass and velocity, remember C is speed of light, mass times velocity is equal to this constant, Planck's constant, over the wavelength of light. So another way of relating various variables to one another. The other person we want to talk about is Verner Heisenberg. So for those of you who know modern TV shows, you'll think of another guy when we say the word Heisenberg, but Heisenberg probably comes from this gentleman, Verner Heisenberg, and he has a principle called Heisenberg's uncertainty principle, very famous principle in chemistry, that says we are unable to know the exact position as well as the speed of a subatomic particle, notably electrons, at the exact same time. So why is that? Why can't we know the location and speed of an electron? And here's the issue. When you go to measure something like an electron, you need to be able to see it. You need to be able to observe it. But the act of observing it, maybe we need to shine a light on it, right? We need to look at it. And when you shine a light on something, you strike with a photon. But the problem is that a photon is the same mass as an electron, right? They both weigh pretty much nothing. So if you bombard this electron with something that weighs the same amount as it, you're going to knock it off course. And so you might be able to measure its speed, but if you measure its speed, you're going to knock it off balance and you're not going to know its location. And you might be able to measure its location where it is, but if you do that, you might need to bounce something into it that's going to speed it up or slow it down. And so his principle says that you can't know both of those things at the same time. You can know where something is, but not how fast it's going, or you can know how fast it's going, but not where it is. And so on your note guide, there's an interesting question that helps to illustrate this. It says, suppose that you measure the temperature of a cup of hot tea with a cold thermometer. How does that cold thermometer help to illustrate this Heisenberg uncertainty principle? And if you think about it, when you stick that cold thermometer into the hot tea, the very act of putting that cold thing in the hot tea is going to lower the temperature of the tea just a little bit, right? Because it's going to have to require some of the heat from the tea to heat up that thermometer. And so the very act of measuring your beverage actually changes its temperature, and so you can't get an accurate reading because you have to change the initial thing based on your measurement tool.